Today guys, in today's video we'll be talking about stoichiometric calculations. Stoichiometric calculations are important for determining the amount of reactants and products in a reaction. By using the ratios of substances in a balanced chemical equation, it is possible to calculate the required quantities for either the reactants or the products. So by the use of stoichiometric calculations, we can find information either about the products and the reactants by following certain rules, and this can only be done after balancing a chemical reaction. So remember, make sure that your chemical reaction is always balanced, because it will be pointless because you won't be awarded any marks, because your answers will basically be based off that reaction and it's unbalanced and you're not going to get the correct answers. So always make sure that your reaction is balanced, unless they say in the description of the question or of the reaction they say it's balanced, then you sort it. But if they don't mention it's balanced, sometimes it can be balanced but without them mentioning, just always double check that it is balanced. And we'll be looking at certain subtopics that fall under stoichiometric calculations, such as limiting reagents, percent yield, percent purity, molecular and empirical formulae, and titrations. So, limiting reagents. In a chemical reaction, the limiting reagent is the reactant that will be completely used up, and this determines the amount of product that can be formed. So, in a reaction, the amount of product is all determined on the limiting reagent. Conversely, the excess reagent is the reactant that is not completely used up in the reaction, so there will be left over. And then identifying the limiting reagent is very important in stoichiometric calculations, as it does determine the maximum amount of product that can be formed. To determine the limiting agent, one must compare the mole ratios of the reactants used in the reaction with the mole ratios given by the balanced equation. So you need to first calculate the mole ratios. You need to first calculate the number of moles, use the mole ratios, and see which reagent is limiting. Then percentage yield. Percentage yield or percent yield is a measure of the efficiency of a chemical reaction. So how well did the chemical reaction perform? It compares the actual yield of a product to the theoretical yield, which is the maximum possible amount of product calculated from the balanced equation. So when you do reactions, right, you have to do calculations and determine what is the expected amount that should be formed, right? And during reactions, it doesn't always go perfectly well, because let's say some reactants don't react fully, or some is impure and cannot react fully, so that causes a change in the amount of product formed, and that will be the actual yield of the product. So we must find out the percentage of how much actually was formed based on a theoretical calculations and the actual yield of the product. Then we have percentage purity or percent purity. Percent purity indicates the amount of specific pure compound in an impure sample. This measure is essential in determining the quality of chemical substances, especially in pharmaceuticals and industrial processes. So if you have a substance, right, it's not 100% pure, unless there is possible also call it scenarios, but most manufactured products are not 100% that or 100% that. It's a mixture of different things. So if we have a product and we have a compound in there, most likely it won't be 100%, or that compound won't be 100% made of this compound. The product won't be 100% made of the compound that you're looking at, because there's other impurities that the compound that the product consists of. And then we have molecular and empirical formulae. The empirical formula represents the simplest whole number ratio of atoms in a compound, while the molecular formula gives the actual number of atoms of each element in a molecule of the compound. Determining this formula involves using the percent composition of each element in a compound. So here we have the step-by-step process for determining empirical formula and molecular formula, right? So step 1 states that we need to find the mass. So we assume that the mass is 100 grams overall of the entire compound, and to use the percentage composition directly as grams. So they will most likely give you a percentage, so they say 5% carbon, 10% hydrogen, 20% oxygen, whatever, and must obviously the percentage must add up to 100, and we directly convert that into grams. So if it's 59.75% carbon, that's going to be 59.75 grams of carbon, right? Then it says find the moles, convert that mass of each element to moles using the molar mass. So convert the mass into moles. We all know how to do that. And then it says number 3, determine the simplest ratio. Divide the moles of each element by the smallest number of moles obtained to find the ratio. So if I have 5 moles of carbon, 10 moles of oxygen, and let's say 2 moles of hydrogen. Hydrogen has the smallest amount of moles, so I'm going to divide that amount for each element. So carbon, I'll say 5 divided by the 2, then I'll take the oxygen 10 divided by the 2, and I'll take the hydrogen 2 divided by 2, and then get the ratios, right? And then we write out the empirical formula using the ratio to write the empirical formula. And then number 5, it says determine the molecular formula. Calculate the molar mass of the empirical formula, right? The formula we just found. Find the molar mass, okay? After you find the ratios, and divide the given molar mass. So normally in the question they will give you a molar mass of the compound, of the true compound in its proper ratios, right? And yeah, so we divide this by the value to find the multiplier. So if I divide it, say, and it gives you a a number of 2, so that's the multiplier. So that's how much we're going to take the empirical formula and multiply by that number, by the 2, to get the actual ratio, or the not the actual ratio, the actual number of atoms in the compound. And yeah, that is for finding the molecular formula and empirical formula. Then we have titrations. Now, titration is a technique, right? It's a method used to determine the concentration of an unknown solution by reacting with a standard solution of a known concentration. So, definition of standard solution: it is a substance or solution of which we have a precise known concentration. So, with that, we can use to find the different information of the unknown substance, or the unknown values of the substance. So, say now we have calcium carbonate, and we don't know the number of moles for the volume of grams. We can use the standard solution to find it. So titration, again, it is a method used to find a concentration of an unknown solution by reacting it with a standard solution of a known concentration. Then here's some exam questions in which includes all of these different topics that I went through. So this is question 5.1. In an investigation, a learner added 1,5 grams of sodium carbonate, and they give you the formula, the chemical formula of sodium carbonate, Na2CO3, 2 hydrochloric acid, HCl. And remember, hydrochloric acid is a strong acid, just for your information. A volume of 306 cubic centimeters of carbon dioxide gas was formed and collected under standard pressure and room temperature. Take the molar gas volume at room temperature as 24,45 cubic decimeters. Here they state the unbalanced equation for the reaction is as follows. So here, remember I told you they can either let you know that it's balanced or not, or you have to yourself have to go check. So here at least they're being nice and they're telling you, look, it's unbalanced. So go balance that. Okay, so I went online and what came up for one mole of a substance is that the one mole of substance is the amount of that substance that contains exactly 6,022 times 10 to the 23 elementary entities, which are basically things such as atoms, molecules, or ions. Look, I'm on keyboard back. I do not know if that's alright, but it's fine. It's only definitions. We don't need to worry about definitions. We worry about the calculations. It's where the marks lie. Okay, so the next question they say is balance the equation for the reaction. So let's balance it. So how much sodiums do we have on the left hand side? We have 2 sodiums, right? And on the right hand side we have 1 sodium. Okay. So clearly there is a imbalance of sodiums. So what we do is, remember, in physics or anything that involves reaction, basically, you can't add a subscript. You can only add a, what's it now? A big number, basically. So we add a 2 here. Okay, that's a very nice 2. Yo, dangerous guys. I'm basically drawing with the cursor, so please bear with me. I don't have a touchpad. Okay, so here we have 2 now, and now we have 2 there, so sodiums are balanced. Carbons, here we have 1, right? And here we have 1. Carbons are balanced. Oxygens, here we have 3. Nothing else. Here we have 1 plus 2 here. Remember this 2 is saying how much oxygen, so here's 3 also oxygens. Hydrogens, here we have 1. But here we have 2. So we need to add a 2 here. Not add, but put in a 2 here. Oh, better 2. It's getting better, guys. So now we have 2 hydrogens and 2 here, so it's balanced. Then we look at chlorine. Here's 1 chlorine atom, but you see this big 2 here, it says that it's 2 chlorine molecules, or 2 hydrochloric acids. There's 2 molecules of those. So there's 2 hydrogens, but there's also 2 chlorine atoms, right? Yeah, remember there's a big 2 in front, so there's also 2 chlorine atoms, so it's balanced. So this is the balance equation, right? I didn't do this. You can do side calculations where you put down the values of each element and compare the two. You can do it also in your head, whatever floats your boat. In 5.1.3 it says calculate the mass of sodium carbonate that reacted. Okay, so sodium carbonate, use sodium carbonate. We need to calculate the mass that actually reacted. So let's go look at our values again. So they give us 1.5 grams of sodium carbonate, and they gave us a volume of carbon dioxide gas that is formed. Okay, okay. So here when they say the calculate the amount of sodium carbonate that it reacted, it kind of hints at that there is a limiting reactant here somewhere, right? So it wouldn't be wise to use that 1.5 grams of the sodium carbonate, right? Because you see how much it reacted. It's kind of hinting at there is a limit. So either one of these is going to be limiting, right? So, but they do give us values of products, and we know that if they give you a value of the product, at least what is formed, so here volume of pyramid is was formed, so we can see how much reacted to form this. So we rather use the values of the product, and this was of the carbon dioxide. So we have the volume, so the volume is equal to, oh guys, please bear with us, is 306 um, cubic centimeters, right? But remember we use cubic decimeters. So to convert to cubic centimeters, to the cubic decimeters we divide by 1000. So it's 306 divided divided by 1000. Remember, always use your volumes in cubic decimeters. So then that will come as 0, 306. 0,306. Should I put in the unit? Very nice. Very nice, guys. Then I'll even does it. Probably as a trackpad or something to write with. Okay, so we have the volume. And look here, they say take the molar gas volume, right? Vm as 24,45. So this is for gases, remember, and carbon dioxide is a gas. So they gave us the molar volume, right? Okay, and that is equal to what? 24, comma, oh, I think 45, right? So we have volume and we have molar volume. What equation do we know uses this? We know that N equals to, oh, that's a nice N, guys. Equals to V over Vm, right? Okay, and we can use the number of moles and use the ratios to get the number of moles for sodium carbonate, and then we can convert that into mass. So do you understand what we're getting at? So we know the what you call it, the volume, and we said, remember, use the volume in cubic decimeters, which is 0, comma 0,306 divided by the molar volume, which is 24. Remember, it's given. Normally at STP it is what, 22,4, right? I don't even know. Just believe in yourself, you know. And yeah, guys, look at my handwriting skills is getting better with this cursor. Like, look at that. That's perfect. Ish. Okay, and then therefore, whoa, dangerous. Therefore, the number of moles equals, so let's put it in the calculator, 0,306 divided by 24,45, and that equals to a big number. So when you get a big number like this, it is best to round off to the nearest 4 decimals, because we're going to use this again. So don't round it off to the nearest 2, okay, because you're going to get different answers compared to the memo, right? So it's better, it's safer to round off to the nearest 4 decimal places. So that's going to be 0, what's that, 0,01251, but we set to the 4, so it's going to be 0. And remember, the unit of number of moles is just mole. Okay, so it's 0,0125 moles, okay? And remember, we can convert those moles into a mass. But what do we need a mass for? We need it for sodium carbonate. So let's use the ratios. The ratios between sodium, alright, and carbon dioxide, right, it is 1:1. So it has a ratio of 1:1. So if I have, that's supposed to be dotties. If I have 0,125 moles here for carbon dioxide, then sodium carbonate would also have 0,125. I'm not rewriting here. So yeah, so we now have the number of moles for sodium carbonate. Okay, so I just tied it up a bit. So we have the number of moles of carbon dioxide, and then we said therefore the number of moles. So this is how I would write it, the number of moles of what substance? It is sodium carbonate. Need to indicate it's supposed to be a subscript in a 2CO3 equals to also 0,0125. Okay, and we have the number of moles, and we can also convert that into a mass, right? We need to convert it into a mass, so we can use the equation n equals small m, which is your mass, which is your mass. So I don't know why I think they don't want to throw over molar mass, right? Um, we have what you call it, the number of moles, and we can get the molar mass. We want to find the mass that was used. So we can just change the subject of this formula. So m equals, remember to get m on its own times big M on both sides, and that's going to equal to n times big M, right? And we know the what you call it, the number of moles, so that's going to be 0, 0.0125. Yo, it looks like a lot, not gonna lie, my handwriting is getting worse, so I don't know what's happening. Oh, that's funny what that is. Oh, and that is applying. So what is the molar mass of sodium carbonate? So there's two sodiums. Sodium is 23 plus 12. So 23 times 2, which is 46, plus 1 carbon, which is 12, plus 3 oxygens, which is 16 times 3, which is 48, right? And that equals to 106. So the molar mass is 106 grams per mole. Then we just times that, right? Times those two numbers, and we get to 1,325 grams. You don't have to round it because it's only 3 digits, so it's not, you're not gonna get anything out of it. So yeah, there we have the mass of sodium carbonate, and that would be your final answer. So your final answer would be 1,325 grams. Okay. Okay. Next question, 5.1.4. Determine the percentage of sodium carbonate in excess. So they want to know how much is in excess. So how much grams, percentage of how much grams was not used, how much was not reacted. So they gave us a total amount of sodium carbonate, and we calculated how much reacted, so we can now find how much didn't react and convert that into a percentage. So what we do is we take 1,5 minus 1, 1,325, right? That's then equal to 0,175 grams. Okay, so this is how much that didn't react. This grams here. This is how much that didn't react. So to convert this into percentage, you take how much didn't react divided by the total amount of the compound, right? And then times by 100. So then we'll say percentage. Oh, that's very, very ugly. So you take percentage. I'm trying to cursor with the mouse. Oh, don't play with me. Oh, okay. You can do my G. It's alright. It's alright. Equals um 0,175. So most of my time is being wasted on trying to throw uh, times 100, right? And that would give you, so 0,175 over 1.5 times 100, and that gives you a percentage of 11,66666. So here we can just round off to the nearest two decimals because that's our final answer. 11,67%. And that's your final answer. So that's it for 5.1. Okay, We have question 5.2 following 5.1. It states that in an experiment, 8 grams of unpure aluminium is added to an excess of sulfuric acid. The following equation occurs. So here we have aluminium with what you call sulfuric acid, gives you aluminium sulfate and 3 moles of hydrogen gas. Okay. Look here, look here. When you see this, right? When you see this word unpure, right? Don't use any values that is associated to this compound. So if it said here unpure aluminium and it says it's 8 grams of this unpure aluminium, do not use this 8 grams anywhere unless needed. Okay, unless it's a final answer of maybe percentage purity, right? Do not use this 8 grams because it's unpure, so you cannot use it. Okay. Here it says added to an excess of sulfuric. Here they're giving you nice hints, they're giving you subtle hints. Excess, we know that the sulfuric is in excess, so we know that the aluminium is going to be the limiting, what you call it, reactant. Okay. Sulfuric is in excess. Okay, and they also tell you the volume of the hydrogen gas produced is 6,72 cubic decimeters at STP. Calculate the percentage purity of aluminium. Okay, the only values we have is the 8 grams and the 6,72. We know for a fact, we cannot use it 8 grams. So they're basically forcing us to use the 6,72 cubic decimeters volume, whatever. But what we can attach to that is STP. Okay, I came back and it stated that the value is in fact 22,4. Remember, I was unsure and it is actually 22,4. Okay, so now we have two values that I can remember. And when it says STP can only be associated with gases. And the only gas we have here is the hydrogen gas, right? Says literally says here hydrogen gas, and they give us the volume. So we have the volume, right? And let's remember in cubic decimeters, but we also have the molar volume. So remember, STP is a molar volume, and it is, remember, 22,4 cubic decimeters. Alright, and the only formula that can utilize these values is the N equals V over Vm. So remember, we convert this, also remember to convert this into moles. So we have to use this formula, right? So we take the volume, given volume, for the volume. Oh, it's a dangerous number. Sorry, that is 72 over 22,4. Whoa! Check this out. Check this out. That is probably I want to stick me. Okay, and what does this thing give you? Let's just put it in. 6,72 divided by 20. How much you want to bet? 10 million rand on the board right now. It's going to give you a nice number. What did I tell you? It's going to give you a nice number. 0,3. When I say nice numbers, I mean it's not a lot of recurring numbers, or it's not an ugly number, it's nice, it's simple. Yes, it's not a whole number, but it's simple. So it's 0,3 moles, right? And yeah, we can use this elsewhere in the reaction because this is actually the number of moles formed by hydrogen gas. That's not in excess, there's nothing limiting, this is actually the amount that is formed. And we can use that and use ratios to get the actual number of moles of aluminium, because remember we want to find the percentage purity of the aluminium. So we use ratios. So for the ratio between, whoa, it's a funky A there. aluminium and hydrogen gas, it is, what is it now? 2 to 3, 2 is to 3, right? So here we have what you call it, the number of moles for hydrogen, then we need to find the number of moles of aluminum. So we basically want to find 1/4. Because remember, here, this 3 means there's 3 parts, right? And of the 3 parts, 2 parts of aluminium is used, you understand, to form the 3 parts, if you like understand what I'm going to say. So we basically want to turn this value, the 0,3, turn into 1 part, right? And then we times it by the number of parts aluminium is needed, okay? So we take the total number of moles divided by the ratio numbers, the mole numbers, which is this 2 and 3. So we're going to divide it by 3 because that's the moles for mole ratio for hydrogen, right? And that's going to give us 0.1. At 0.1 is the number of, or not, that's the number of moles for 1 part, okay, in this reaction. We want the number of moles for 2 parts because we want to find aluminium. So we just take that times 2, and then you get 0,2, right? 0,2 moles. And now we have the number of moles for aluminium. So we have the number of moles for the aluminium, right? Oh, coming back at is that. Hello, can you still come right? Okay. So that's the number of moles for aluminium, right? What was the number again? 0.2. Okay, so we have 0.2 moles, right? And now we can convert that moles into a mass. So the only equation that is gonna be utilizing moles, and remember we also have the molar mass, is n equals small m over big M. So this small m is basically the amount, the mass of aluminium that actually reacted, that was actually pure enough to react. Because remember, only pure substances can react. Okay. When I mean pure substance, I don't mean pure as whole, but the pure components of that substance can only react with pure atoms, whatever nonsense, whatever. Yeah. So remember, we're trying to find the mass, so let's change the subject of the formula. And that is, remember, times big M on both sides to get M alone. It's going to be N times M. Okay. We have the number of moles. 0.2. That is 22 times. Okay, let me just get the molar volume of aluminium. Aluminium is in, what is this? Row 13. Yeah. And that is 27. 27 um, grams per mole. So remember 27, and just put that in the calculator. Whoa. Get a load of this freaking thing. Oh man, I can't make it equal sign. Okay, so mass equals, so 0.2 times 27, and that equals to 5,4. Not a bad number. Check my 5 here. Looks like it's Jack Sparrow had a cat. If the 5 had a cat of Jack Sparrow. Okay, so we have the pure mass of aluminium. And now we can find the percentage purity. So remember, the percentage purity, it is the percent of the total pure mass in a impure substance. Right? If you understand what I mean, you know. So now I must make this out. Percentage purity. I'm not gonna edit it. You're just gonna watch me like this. We have to write it out, Spanish. We have to write it out. Because if someone needs to know what is this to do. So sure, that is equal to the amount I'm gonna say actual pure and over impure. So it's pure mass. I'm just gonna put the values in over the impure. And lucky enough, I did tell you that it is impure. So like so you know what is the impure mass. So you know we don't know it. And because it's a percentage, we times it by 100. 100. And if you put that in a calculator, you should get a value of, let's see if it's a nice number. That's a nice number. 67.5%. And look here.